let's actually make what we just discussed in that qualitative example, let's make it formal and write it down as a principle. And basically all the talking that we just did, that is called the principle of linear independence. And what it means is the X and Y motion is independent on each other, right? So let's formally put this down. So it's called the principle of linear independence. All right, so what that means is motion in orthogonal or perpendicular directions are linearly independent on each other. Okay, I'll explain what does that mean. Motion in orthogonal, and orthogonal is basically just a fancy word for perpendicular. Directions. Are entirely linearly independent on each other. Okay, couple of jargons over here, a couple of words. Orthogonal, perpendicular, most of the time it's just the same word. I'm introducing it just in case you see that in textbooks or something like that. In very, very advanced mathematics, there's slight difference to it, but you'll never encounter that, so you don't have to worry about it. Another word is linear independent. Well, independent, you know what that means. They don't affect each other. Linear, just it's again, you don't have to worry about that. It's unimportant for now. If you take more math classes, you might encounter subjects called linear algebra, and it means something more specific there. And okay, so with this, what are some examples you can solve? So these are some things we are going to solve. So for example, we can say if I have a basketball and I want to shoot it at a hoop somewhere, let's say that is let's say 4 meters away and 10 feet tall from there. So you can ask a lot of questions. We're going to analyze this as, for example, so at what velocity should I launch the ball with? What speed should I launch it at? And what angle should I launch it at? So at the end of this lesson, you'll be able to, just from looking at that, right? Looking at if you know how far you want to get the ball from here to there, you know exactly what speed you need to launch it at. If you play golf, right, you can see if my hole is over here, and so what if I hit it with or in general you just want to move it as far as possible. If I hit it with certain amount of velocity and the angle, then where will it land? How far can I get it, and how long does it take? Right? So what will the displacement be of that ball? You can also try to launch an object, right? So if you want to launch an object over a hill that's let's say 100-meter tall, right? You want to launch maybe a cannonball over it, right? So what angle, what's the minimum angle and velocity should you launch it with, right? So these are things we can go ahead and answer. And a lot of this is actually, believe it or not, it looks like very, very basic examples, but all these equations are the almost exact same equations you use to even launch a rocket to Mars or launch a rocket to the moon. So people say rocket science sounds like something very complicated. Actually, it's very simple physics. You will learn 80% of it in basically the next hour of this class. All right. So this is just me formalizing the principle, and in practice, what we basically need to do is this. So in practice, what you need to do is just analyze the X motion and the Y motion, so the horizontal motion and the vertical motion almost independently, okay? And you can basically just apply the Suvat equations separately. So instead of doing this, which you're now familiar with, how to analyze one-dimension motion, you duplicate it once, okay? And then you put in a subscript over here. So that's the X and that's the Y. So you analyze all the X motion and the Y motion independently. And if you can do one dimension, you can do two dimension. That's the whole point. And the only other thing to note over here, I will use a different color to draw attention to it right from the beginning, is this. Notice I did not put an X and Y with time because displacement is a vector. Velocity, initial and final velocity are vectors. Acceleration tells you which direction the velocity is changing. So and how much it changes. And so it has a magnitude and direction as well. It tells you how much the velocity changes and in which direction does the velocity change. Does it change forward or backwards or sideways, right? So these are vectors, but time is not a vector, right? The fact that you might say, well, time can go forward and backward. Well, not really. Time increases and decreases, yes, kind of forward in time and backwards in time, but it's not a physical direction. It's not like time is moving in the north direction, right? That's completely nonsense. So be careful of that, right? Don't think that when something just increases and decreases, that means it has a direction. When we say direction, we mean physical direction, like spatial direction. You cannot say the time in the northward direction. The time in the north direction and time in the south direction is exactly the same. The time in the east direction is the same as the time in the west direction. There's no direction, okay? So what that means is whatever happens to X at a certain amount of time happens to Y in the same amount of time. So this has to be the same, all right? So we'll see examples to make that concrete what that means, right? But just roughly, for example, just to get you start thinking about it, right? It's the time it takes for the ball to go up and down, right? In this path, right? From here to here, the time it takes for it to go to its highest point and its lowest point is the same amount of time it takes from it to go from the initial X to the final X location, like that, right? So I should say the time it takes for it to complete this path in the Y direction is the same as the time it takes for it to complete this path in the X direction. All right, it sounds stupidly obvious when I say that out loud, but translated mathematically, that's what it means. It means there's no two different times. Okay, we'll see some examples and that makes it concrete.